Good morning, everyone. So let me just wait for a few more minutes till people join in. So I would like to know, like, how is your workload level? So I will ask one representative from computer science and engineering program, and one from math and computing, and one from like the MTech program to speak up. So if anyone wants to volunteer from computer science and engineering, just want to know how your load stands right now, this course and other course. Is there anyone who would like to say something? Okay, so I would presume that things are not too bad then for computer science and engineering. How about is the class rep of computer science and engineering here? Raghavendra is not here. Okay, how about math and computing folks? I see. Okay. I guess, Aditya, you really have to increase the volume when you're listening. So next time, next video onwards, I will try to speak loudly. Okay. Noted. So how about math and computing workload? Are things fine? Any comments? All right. So finally, in the MTech, PhD, CSE, Rohit, or anyone has to say something. Is things okay with you in the course load level and things like that?
Sir?
Yeah. So I just asked, how is the course level, workload level?
So we have one quiz this Saturday, two quizzes next week, along with two more presentations, and that does not include the maths quiz. So I think we are a little jam-packed. Hello?
I will see what I can do to help, but just wanted to know where you stand.
Okay, sir.
So you are saying that it is too heavy.
Lots of assignments and quizzes this week, or at least next week, yes, sir. Two presentations, three quizzes, and one quiz this week. So three quizzes, three presentations upcoming in the next 10
Okay.
days.
Yeah, I think presentations are quite hectic because you need to. Yeah, all right. Yeah, thanks. Okay, so that's about just what I wanted to see how people stand. All right, so let's get started with today's class. So I thanks Aditya for pointing out the volume was too low. Let me next time onwards I will try to speak a little more loudly. All right, so if it is too bad, then if everyone feels, then I will re-record again. But yeah, try to adjust with that. So let's see. Okay, so moving on. So let's just start today's class.
Sir, before we start, just one question. In yesterday's class, you announced that we'd have the exam, the NSEM exam on 17th December, right, sir?
Yeah, yeah.
And it would be a 3-hour exam, you said, right, sir?
Yeah. Yeah, that's correct. So this is the schedule that has been tentatively fixed by the academic committee, academic office. I think it will. This will get finalized.
Okay, sir. And
Yeah.
again, I mean, not to, I mean, in the mid-sem, you said 2-hour exam. Can we have like slightly shorter exam for the mid-sem?
No. This is not governed by me. So
Oh,
these are
okay.
things that are the institute specifies. Okay, so I was planning to have 3 hours exam in the midsem itself, and then someone told me that midsem has to be 2 hours. So that's the reason.
Oh, okay, sir. Okay, sir.
Yeah.
So, but can you at least keep like 5-10 minutes for scanning and uploading some extra time?
Yeah,
I
we
mean,
can do
depending on
that.
how many
Maybe.
questions we
Yeah,
have.
maybe we can start at 9:30 to 1, something like that we can do. Because I can't go beyond 1 for sure, because some people might have an exam at 2 o'clock.
Oh, okay. Yes, sir.
Yeah. So let us see. We will think of something.
Thank you, sir.
Yeah. All right, so this is what the NSEM dates are. So let's anyway. So if there are no other questions related to these things or anything, let's get started with today's topic. So what we were seeing yesterday. was maximum likelihood estimators. So I understand that I have unintentionally omitted some things in central limit theorem, some easy things which Sitsiklis teaches. So I'm going to make a offline video for all of you to watch, which is going to be quite easy. But in the interest of learning something new, I'm going to talk on my estimators in this class. So let's see, someone has a message. All right, apparently not. Okay, so we were looking at maximum likelihood estimators. Okay, so what we saw yesterday was a very simple example. We saw that if you have a coin toss, a coin with bias P. Okay, so this is the coin bias. Okay, and let us say this is unknown. You don't know what is the actual probability of getting heads. Okay, and then what you observe is you observe the observations. We call the observations typically as small xi's. Okay, so let us say, so you have three observations. So x1, this was let's say head. Okay, and we are going to call head as 1. Okay, then x2 is equal to tail, which is 0, and then x3 is equal to tail, which is 0. So we saw this, and then we asked what is the probability of getting x1 equal to 1, okay, x2 equal to 0, x3 equal to 0, given that, given, I shouldn't say given. Okay, this is a thing that is getting confused. When I say given, you will think it is that we are talking about conditional probability, but this is not that. What we are saying is this is parameterized by saying that the coin has a bias which is p equal to 0. So we saw this yesterday. So we saw that this one, this probability is going to be 0. And this function is called as likelihood. Okay, and it is denoted by capital L. Okay, and it's a function of the parameter that you are trying to learn, which is small p in this case. Okay, and then we also did for another example, we did some few points, we did this here. So we looked at, for p equal to 1, we said this is also 0. So essentially we studied this, and then what we said is the likelihood, okay, L of p, as a function of p, the choice of p that you make has a shape which is like this. Okay, and this is half. It peaks at a value which is going to be 1/3. Okay, so this you can do it at your house, and you can test for this values of p. Okay, so you can do a small Python program to actually plot this. All right, so now basically this was what it was. So now what we are trying to come up with is a systematic procedure to find out this point. Okay, so the value 1/3. Okay, so let me write here, the value 1/3 is called as maximum likelihood estimate. Okay, because that is the value which maximizes the likelihood function, which is a function of p. Okay, so let's try to summarize it. So basically, PMLE is going to be that value of p. So when you say argmax of p, L of p, right? So basically, if you do, let me just try to explain what this means. So if you do max of some numbers, so let us say I have a function which is, let's say, max of sine theta. Okay, and theta takes a value between let's say 0 to pi/2. Okay, so what is the maximum value that you for this? Yes, for max of theta, max of sine theta in this range.
1.
1, yeah, thank you. So this is max, but if I do something called as argmax, okay, so if I do this sine theta, I am going to get a value which is pi/2. Okay, so basically argmax is going to tell which argument of the function, this is called as the argument of a function, maximizes the function, right? So similarly, PMLE is going to find out which argument P maximizes the likelihood L of P. Okay, and in the particular example, okay, by a Python program, let us say, okay, if you do this by a Python program, we can say PMLE is equal to 1 over 3. Okay, if you do the Python program and if you actually plot it, you will see that it is maximized at 1 over 3. Okay, so now this is a program. If you can write, you can do this, you can get through simulations. But ideally, if you want to do this like theoretically, you want to get an analytical formulation for MLE. So that is what we are going to do that for. First, we will do it for Bernoulli parameter. Okay, so let's do that. So let us say there are n. So now let's write MLE, maximum likelihood estimator. We are trying to derive the estimator. So estimate is a value that an estimator takes. Okay, so so what is an example of an estimator? This is like x1 plus x2. You know, this is one estimate that we saw. Okay, for the mean. This is an estimator. The value that Mn takes. So Mn can be, let us say, for a particular value, it could be like I don't know, maybe 2.1. So this is called as an estimate. So this function is called as an estimator. Okay, and the value is called an estimate. Value attained is an estimate. It's just a simple definition, just so that you understand the difference. I don't think it is too complicated, but it is important to clearly distinguish this. All right, so now we are trying to find out maximum likelihood estimator for Bernoulli parameter. Okay, so this is what we are trying to do. So what we are going to say is, so there is some data given to us. Okay, so that the data is values, like you are going to do n trials. So we'll call this as x1 to xn. These are the data given to us. Okay, and this will be equal to small x1. This will be equal to small xn. So basically, these are random variables. Capital things are random variables. Okay, and these are the particular values that you see. Okay, so let me try to explain this. In the previous example, we saw that x1, x2, and x3 we saw in the previous example. The value that we got was 1, 0, and 0. Okay, so the small things represents the particular values. The capital things represents the random variables. Okay, I hope this distinction is clear. Okay, now we have to do all the steps that we did previously and try to come up with the maximum likelihood estimator. Okay, so now what we are going to say is, if the ith trial, okay, if it was 1, so what is the probability that this happens given that the parameter that we are interested is in P? So you remember, right? So what we did was we did L of P. Okay, so now if our data is only consisting of a single ith trial where the output was 1, L of P will be the likelihood, which is the probability that this happens, right? So this will be equal to P. Okay, so what if let's say some trial xj is 0? Okay, so then here, if you remember, right, we looked at P, and this will be like 1 minus P, right? So that's what we did, and that's how we got those values. So xj equal to 0 will be, if there was a trial j which gave a value 0, this will be 1 minus P. Okay, so in general, if you want to find out the likelihood, this is going to be probability of obtaining a particular sequence, x1 equal to x1, x2 equal to x2, x3 equal to x3, and xn equal to small xn, given that you are, sorry, I shouldn't say given, it is parameterized by P. Okay, so this is what we have to understand, that this is the likelihood. Okay, given the parameter P, what we want to find out, what is the chance that you obtain this sequence. Okay, And since we are not making the distinction like we don't know what is the actual value of x1, right? So what we are going to do is that we are going to understand that this is actually, since all the trials are independent, we can actually split this up. Since they are independent trials, we can split it up. Okay, and we will write this as, I don't know if you have seen this notation. This is called as product of I equal to 1 to n, p xi equal to small xi given p. Okay, so you would have seen the summation notation, right? So this, whatever comes in the middle, so let us say this is ai, okay, I equal to 1 to n. This is going to be like a1 plus a2 and so on, right? So in the product notation, if you have pi I equal to 1 to n of some bi, this is going to be like b1 into b2 all the way up till bn. All right, so let me repeat. So what we saw is, if you have a parameter p, okay, so what we did in the previous example was we plotted it, okay, and we plotted L of p like this. But in general, we wanted a closed form expression. So that is why we are looking at, given the parameter p, what is the probability that you obtain the sequence x1, x2, x3, small x1, x2, x3, and so on. And since they are independent trials, we can split it like this. All right. And then further, we can simplify and write it in terms of this product notation. So now with this, we are ready to write what this should be. Okay. So this will be I equal to 1 to n. Okay. P of xi into 1 minus p of 1 minus xi. Okay. So now this is where you will get slightly confused. So let me try to preemptively tell what is this going to do. Okay. So let us take some examples and get this clear. Example. So let's say n equal to 3. Okay. And let's say small x1 is equal to 1, small x2 is equal to 0, and small x3 is equal to 0. Okay. So now L of p will be, so let us try to do this. So what is that? P to the power of x1. Okay. So x1 is equal to 1. So p to the power of 1 is p. Okay. And then 1 minus p to the power of 1 minus 1. So this will be 1 minus p to the power of 0. So this is the first term into, okay, the second term, p to the power of 0, because x2 is 0, into 1 minus p to the power of 1. Okay, this is the second term. Then p to the power of 0 into 1 minus p to the power of 1. So if you really look at this, this is going to be p into 1 minus p whole squared. So this is L of p. Okay, so this is one way in which you can get. We can also look at one more example. Suppose if x1 is equal to 1, and then x2 is equal to 1, and x3 is equal to 1. Okay, so then L of p will be p into 1 minus p to the power of 0 into p into 1 minus p to the power of 0 into p into 1 minus p to the power of 0. Okay, so that will give us pq. All right, so I hope this is clear how this actually simplifies into the desired likelihood. Is there any question here? So can I just quickly check if people are following me so far? Can I have a poll? Okay, so see, the main issue with this likelihood is it's a kind of a confusing thing, because there are, you should understand that what you are trying to maximize. So essentially likelihood is a likelihood. So let's summarize this in some way. Okay, so likelihood. So what is this? It's a function of unknown parameters, right? It's a function of unknown parameters. Okay. And then given a value, given a fixed value of parameters, Okay, so if it is discrete, okay, if it is discrete, what you get is basically probability that you see x1, x1 equal to x1, okay, then x2 equal to x2, and all these things given that parameter. So parameters typically are represented by theta. Okay, if it is continuous, we will see that. Okay, but that's what it is. So given a fixed value, it is representing the probability for a discrete. Okay, and MLE is going to look at which parameter maximizes this probability. Okay, so now let us come back to the problem at hand. Okay, so we came up with the likelihood for a parameter P, and we said that this is equal to I equal to 1 to small n. Okay, so this was Pi to the power of xi into 1 minus Pi to the power of 1 minus xi. So this is what we have got so far. So let's try to maximize this. Okay, so now if you have to maximize a function, okay, so like if you look at the likelihood function, no matter what set of data you are looking at, it will have a shape like this. Okay, and there will be a maximizer at some here, which is called as PMLE. Okay, so this will be the maximizer. Now you have to make an observation. See, so this is something that you would have learned in your calculus, but I'm repeating here. So if a function, if you have a function like this, which has a single maxima, so this is called as a maxima. Okay, so if there is a function which has a maxima like this, okay, and you want to find out where it is obtained, so you can observe one thing, right? So at the maxima, if you look at the slope, at the maxima, the slope is equal to 0. Okay, at maxima, the slope of L of P is 0. Okay, so for functions which have a single maxima like this, okay, so at the maxima, the slope is 0. So what is the meaning of slope? Yes, how do you find out a slope of a function? Can someone tell me?
Differentiation.
Yes. Yeah, so basically what you need to do is, if you take the derivative of L of P with respect to P and set it to 0, okay, and find the P which solves this, find the P which solves it, we are going to get the MLE estimate, MLE estimator. Okay, we are going to get the MLE estimator, maximum likelihood estimator. Okay, so now if you want to differentiate this particular function like this, you have to use product rule, which is going to be quite complicated. So therefore, what you do instead is that you take the log and then differentiate it. So basically log does not change. So log is a one-to-one increasing function. Okay, so it will not change the maximizer. So maximizer of, so let me try this. So argmax of LP is going to be the same as argmax of log of LP. Okay, so this I think you can understand, because log is going to be an increasing function. So with that idea, what we do is, we, instead of taking the likelihood, we are going to take the log likelihood. So for those of you who have read a little bit of machine learning, or if you are seeing AI, you might have seen this used. So anyway, so this is the log likelihood, and it is represented by a small l. So L of P is going to be log of L of P. Okay, and the base, if I don't specify a base, it's always going to be base E. Okay, this is called as a natural log. Okay, so let's just use some color, different color for change. So now what is going to be L of P? So when you take a log of a product, what happens? You get sums, right? So you are going to get this as sum over. So xi is anything that comes to the power that comes out. So basically let's recollect the rules of log. So log of AB is log A plus log B. Okay, and then log of a power some k is equal to k log a. Okay, so using that idea, when you put log here, this entire thing becomes a summation. Okay, and the PIs, yeah, so the PIs will become xi log pi. Okay, so let's write that. So if you do this simplification properly, you'll get xi log I'm sorry here. So nobody told me. So this p is a single number, right? So this is not pi. So this is p. Okay, so let me just erase this here. Because you are fixing a single parameter. It's not that you are having different values. Okay. So there is no pi. There is only xi. Okay. Yeah. Anyway, so this is xi log p I equal to 1 to n plus. So I think before we can do the simplification, we need to do some more simplification of LP itself. So let us do that first. So LP, the thing here, so it is going to be, let us write that, it is going to be P into x1 into 1 minus P into 1 minus x1 into P into x2 into 1 minus P into 1 minus x2, right? So we have all these things, P into xn, P to the power of xn into 1 minus P to the power of 1 minus xn. So we have things like this. So if you can see this properly, you can group all the P terms together. So this will be P into summation xi, okay? And 1 minus P terms you can group together. This will be 1 minus P into all of these 1 minus x1, 1 minus x2, all of this becomes n minus summation xi, okay? So this is a useful simplification. And then we will take now the log of this. So the log of this will be small l of p, right? So small l of p will be summation xi log p plus n minus summation xi log of 1 minus p. Okay. So now this is the log likelihood. So this is the log likelihood. So in order to find out the MLE estimate, we need to take the derivative of this with respect to p and set it to 0. So dLP by dP, if you take the derivative, you will get summation xi by p, because some xi's are constant, plus n minus summation xi divided by 1 minus p, okay, and then applying the chain rule, you will have into minus 1. Okay, so now if you set this to 0, okay, and then we will simplify this and try to solve for it. Let's see. So what we will get, you will get summation xi by p is equal to n minus summation xi by 1 minus p. So let's do some simplification again. So you will get summation xi minus p times summation xi is equal to np minus p times summation xi. Okay, so np, yeah, so this is fine. So now you can see that these things will go. So now we get, so whichever solves this, so this p will be the MLE estimate. So p MLE will be equal to this p, okay, this p itself. So this is going to be summation xi by n. So if you observe this, this is the PMLE is actually going to be the same as your MN, the estimator that we had been seeing earlier. Okay, so let's quickly go through all these steps once again, because this might have been slightly confusing. See, the whole idea that you are trying to find out is, in real life, you don't actually see the model. What you see is data, right? See, for example, what you spend in Amazon, what you spend in Flipkart, or what you spend in your grocery stores, that is not coming from a distribution. You don't sit at home and do a coin toss and then see, okay, this came head, so let me go and buy a curd or something like that. You don't do that. What you do is you just go and buy. And then later, you can actually look at all the data that someone has and then try to find out what could have been the model which generated this data. Okay, so that is the idea that we are trying to solve. We are trying to come up with a model that was not known to you. So this is why machine learning is useful, right? So you look at the data and you find out, okay, this must have been what the model was, and that is why this was purchased. So now with this idea of a model, then you can do a lot of interesting things, right? So the same concept we are now learning in a very simplified setting. What we are looking at is basically a sequence of coin tosses. So that the coin tosses that we saw was with 3 coin tosses, 100 example we saw yesterday. Okay, in general, if you have to solve, there will be n tosses given to you, and you are supposed to find out the hidden parameter p. Okay, and what we did is we understood that to arrive at that, the probability that you see a sequence of coin toss is given by the likelihood. And this is what we got for the Bernoulli parameter. In order to find out the maxima, we made the observation that at the maxima, the slope will be 0. Okay, and slope is nothing but the first derivative. So that's why we took the derivative of the likelihood, and that was we took the derivative, but taking the derivative directly is a problem because that will involve product rule. So instead we took the log and then took its derivative. So that's why this log likelihood, you will see it appears in machine learning all over the place. Okay, so when you take the derivative and then when you solve for it, the value of p which maximizes the derivative, which solves the derivative equal to 0, that is nothing but the MLE estimator, and that turned out to be summation xi by n, which is the same as sample mean, which is the same as the estimator that we had seen earlier. Okay, is this okay? Everybody follows this?
Yes, sir.
Okay, good. All right, so moving on, there is a so this one I will probably leave you to read. There are some things that you can do here. So maybe we will do one another example just to get an idea of how the estimator will in general work. Okay, so let us look at MLE estimator for normal distribution. So we saw an MLE estimator for Bernoulli. Okay, so we saw MLE for Bernoulli. Okay, now we will look at, so the Bernoulli is a discrete distribution. So let us look at MLE estimator for normal. Okay, so this is the next task. So now what you have is like you have been given x1, x2, all this data xn, okay, has been given to you, which is independent normal. Okay, and now so essentially what is given is like x1 takes a value small x1, x2 takes a value x2, and all this has been given to you. This is the data. It is independent normal. What you are supposed to come up with is mu MLE, the mean estimator, and sigma square MLE. This mean and variance you have to come up with, which is the maximum likelihood estimators for these two parameters. Okay, so this is the task at hand. So now the thing that we looked at basically the estimator earlier, right? So we saw L of P. Here we saw L of P. Now we will see basically L of mu MLE and sigma square MLE. So this is what we need to come up with. We need to find out this. This one, what we will define it to be is going to be basically density that you will see for all of this. So x1, x2, xn given mu MLE and sigma squared MLE. So let me repeat here. This might be kind of confusing. So previously, what was this? So we looked at basically probability. For the discrete thing, we saw what is the probability of getting x1, x2, xn, right? And given the parameter p, that is what we saw previously. But now if you remember the idea of density, so what was the notion of density? So we said that if you look at a point X, okay, so if you look at the point X and if you look at the density at that point, which is f of X, okay, so if you take a small interval around here of length delta, okay, so basically what we said is f delta into f of X is going to be equal to approximately be equal to probability that you have basically your random variable falls between X minus delta and X, right? A small interval around X, this small x. So that is the interpretation of the density with the small x. So this is what we saw earlier in the continuous distribution. So using the same idea, instead of looking at probability, we are going to look at the density. Okay. So if the parameters are good, you will get a high value for the density, and that is going to be the maximum likelihood estimator. Okay, it's the same idea. So the density is replacing the probability. What was there in the discrete, the density is replacing it in the continuous. Okay, so moving on. So that means, since if that is the case, what you can also do is that you can, since they are IID, if you remember that joint distributions which are independent. So if x and y are independent joint distributions, so we remember this, right? This will be f of x into fy of y. This we remember, right? So since we are saying that they are independent samples, we can write this as fxi. So I'm going to write these two unknown parameters as theta. Okay, and this will be, therefore L of theta will be equal to this product. Okay, so this is the likelihood for continuous. This is the likelihood for, we have taken the example for normal, but this is true for any continuous random variable. So any continuous MLE will have this form. Okay. Now let's try to solve this for normal distribution. So let's try to solve this. So what will it be? So L of theta, okay, is going to be product. So product I equal to 1 to n. So now I'm saying theta is some mu MLE and sigma squared MLE. So let's say mu and sigma. So what do you get here? So this will be 1 over root 2 pi sigma e power minus xi minus mu by 2 sigma square, right? So this is what is going to be the likelihood, all right, in terms of mu and sigma. So theta is nothing but mu and sigma. It's a shorthand for this is theta. Okay. A shorthand for mu and sigma MLE. See, basically sigma squared. I'm basically introducing these notations because this is the notations that you will see even in machine learning. So I don't want you to get confused later on. All right. So now, as usual, we will try to take dl by d mu and dl by d sigma and try to solve it. But unfortunately, again, this will involve product rule, so we don't want to get there. So let us use it by taking the logs. Okay, instead we will take the log. So let's first simplify this a little bit. So L of theta will be 1 over 2 pi to the power of n by 2. Okay, because n of them I'm multiplying. Then 1 over sigma n e power, you will have summation over all the terms, right? E power I equal to 1 to n xi minus mu whole squared. Okay, because if you see there are many terms, they are getting multiplied together, right? So that's why we get this over 2 sigma squared. So this is going to be the expression that we will take log of. So now taking the log, what do we get? We get the log likelihood L of theta, which is going to be n over 2 log of 1 over 2 pi, which we can write it as 2 pi and put a negative sign, minus n log of sigma. See, there is a negative coming because I'm pushing this on top. I hope this is okay for everyone. Then again taking the log here. So since the log is always to base e, so when you take log to e, you will get only the exponent. All right. This will be minus summation I equal to 1 to n xi minus mu whole square divided by 2 sigma squared. So this is the log likelihood. And now we can take the derivative with respect to mu and sigma. Okay. So if you do that, so let's not do the calculation perhaps, or maybe let's do it. So so now since theta has 2 parameters, we have to take the partial derivatives. So partial derivative of L with respect to mu. Okay, so this has no mu term, this has no mu term. Taking the log likelihood here, what do you get? You get summation xi minus mu divided by sigma squared. This is what you will get. Okay, this 2 and the exponent 2 gets cancelled away. And when we set this equal to 0, we can actually get the mu MLE estimate will be summation xi by n. You can try it out and see later that this is what you get. Okay, and now if you want to do similarly, you can take the derivative with respect to sigma, and if you do that, you will get sigma MLE estimator square will be, if you do all the steps as before, take the derivative with respect to sigma and solve it and set it to 0, the value that it attains, you will get this as summation xi minus mu MLE, basically mu MLE whole squared by n. Okay, so this is what you will get. So this is the MLE estimate for a continuous example. So let me just take a small pause here, because I think we have gone through a whole bunch of algebra and they just want to see if things are okay with the students. So are there any questions? Are the things so far clear with everyone? Can I have a quick poll? So I would be much obliged if you can ask me some interesting questions, because this can be a place where people are confused. So any questions here is actually appreciated. All right.
In case of x1, x2 and all, we took them as independent normal distributions, right?
Yeah, that's right.
So does each of them have the same mu and sigma?
Yeah, so that is correct. So each of what we are saying is just like in your coin toss example, right? We took multiple tosses we did from the same coin, and then we were trying to find out what is the parameter that might have given rise to that. Remember? So the same idea we are trying to do for a normal distribution. Okay, and then we are trying to find out if there are multiple people, like multiple samples from the same distribution, what is the parameter that could have given rise to this. So let me give you an example. Okay, so let us say there is this happens sometimes. Okay, these kind of things happen in real life. So let me give you an example. So statistics is used in codes. So example from legal systems. Okay, from legal systems. So what happens is, there is some chemical which will, so there is let's take an example. Okay, so let's say there is a chemical, I don't know, some chemical, let's say arsenic. Okay, so there is arsenic which is released into this groundwater. Okay, so by let's say by industry, some industry G. Okay, now this has happened over 20 years. So this has happened over 20 years. Okay, then what happens is they observe that the children children who are born in this period, okay, their heights are, so male, let us say male height is 5 foot 2 inches, okay, and the female height is, let's say 4 foot 10 inches, something like this, okay. And now when you look at these heights, you will think, okay, maybe the arsenic has caused these children to lose some height, okay. So then what you do is you basically do a MLE estimate of your mu and sigma, okay. And let us say you arrive at, for male, it is like something like, this is for males, it is 5 foot 2 inches. And then for females, you look at the thing, and then you get a height like 4 feet 10 inches. So this is what you can get MLE estimates from the population. Now, if you really want to find out this, whether this company G has caused any problem, what you do is you look at one more like village which is not affected by this industry, and then you look at their heights, okay. And there, when you do that, it turns out that, let us say this was 5 feet 6 for males, okay, and for females, let us say it was 5 feet 2, okay. So then what you see is, okay, since there is a clear difference and there is virtually no overlap in these regions, okay, these two are like well separated, you go ahead and say, okay, this industry is actually polluted, okay, and then you can find that industry and get money for as a compensation for this this population. So that is the idea, okay. So why did I tell you the whole story? Basically, what you will do is you look at the population, and then you will come up with this estimate of the normal distribution for the men and the women, and then you will compare it with a healthy village, and then you will say, okay, since everything else is similar, these two villages are in the very nearby, and they are having the same economic background, so it must be the case that this industry has actually polluted and caused damage. So that is where MLE comes, right? So you look at all the population, and then you come up with the mean and the variance, and that's how you estimate this. So that's how MLE is coming. So did I answer your question? Who was it that asked me this?
Tanuja, sir.
Yeah, so Tanuja, does it make sense what we did?
Yes, sir.
So this is why we are using MLE. Basically, we want to estimate what is the underlying model that gave rise to this particular data, okay? And even though we did a whole bunch of algebra, whatever you get here, the mu and the sigma is quite obvious, right? This is what it must be, right?
Yes, sir.
So that is what, okay. So anyway, so that's good that you asked. So thanks very much. Okay, all right. So if that is clear, let me just tell you one interesting thing about MLE. So now, if you look at this, okay. So let's try to take expected value of sigma MLE square. Okay, so this let's try to do this first algebraically, and then I will try to interpret this for you. Okay, so let's do this thing. So now, what is that? So this is going to be expected value of summation xi minus this mu MLE, right? So let me call it as, since you have seen this Mn, since it is the same as Mn, let me call it as Mn, okay, whole square by n. Okay, so I'm trying to find out, if I take expectation, where will this go to? So Tanuja, where should it go to? If everything is all right, where should it go to? If I take expectation, where do you think it should go to?
Mn, I'm not sure.
Yeah, it should go to sigma squared, the parameter that is actually the true parameter, right? It should go to the true parameter.
Yes, sir.
Yeah. So that is what I'm saying. So let us say it's supposed to go to the true parameter, but we don't know the true parameter. We want to check whether the expectation goes to the true parameter. So that is what we are trying to do here. Anyway, so the true parameter is not known, but we can always take expectations and see whether it really goes to that. So that is what we are doing. And if it goes through, this is called as an unbiased estimator. Okay. So now let's take expectations here. So what we will get, so this will be summation xi square by n. Okay, I'm just expanding this, plus summation mn squared by n minus 2 xi mn by n, right? So this is what it is. Now, if I take expectations, n 1 over n will come out. So 1 over n summation xi squared. Okay. Perhaps we should do some simplification before we do this. All right, it doesn't matter. Okay. All right, so no problem. Then this will be expected summation. So mn is going to be a constant, right? So since whatever that estimated is going to be a constant, I'm summing n of them. So that n and this n will get cancelled. So you will have expected value of mn square. Okay, minus summation xi by n is also going to be mn itself. So this will be 2 times expected value of mn square. So any point during this algebraic computation, if you have any questions, let me know. All right. So moving on. So I have told you that so I have told you that xi is distributed with the normal mu true. Okay, let me not write that, and sigma square. This is the normal distributions things, right? So each of the parameters is coming from that. Now, if you have this, so we know that variance of xi is equal to expected value of xi square minus mu squared. Okay, so expected value of xi square is going to be sigma squared plus mu squared. Okay, so let's do that. So you will have 1 over n summation e of xi squared. This we can do because of linearity of expectations. And similarly, let's try to do this expected value of mn. So mn squared. So expected value of mn squared is going to be variance of mn plus expected value of mn whole squared, sorry, minus, plus. The same way how we did here, okay? So variance of mn, we have done this in the previous class. This is going to be sigma squared by n, okay? Plus expected value of mn is going to be mu square, okay? So that's what it is. So what do you get? So this will be plus sigma squared by n. So there is plus EMN minus 2 EMN. So there will be minus EMN will be winning. So plus mu squared. Okay, so let's simplify this further. What you get is that this will be n sigma squared and n mu squared. So this will become sigma squared plus mu squared minus sigma squared by n minus mu squared. What you get is sigma squared into 1 minus 1 by n, which is nothing but equal to n minus 1 by n of sigma squared. So expected value of sigma MLE squared is going to be this. Okay, so what does this show? So it should have gone to sigma squared, but it is not going to sigma squared. Okay, so this is the MLE estimate for your normal distribution is said to be biased. Therefore, sigma MLE estimator is biased. So you can actually do something better. So you can use a different estimator. So let us say instead of this estimator, you use this estimator S square, okay, which is going to be given as summation xi minus mu MLE whole squared by n minus 1. Okay, if you do this estimator, okay, this is a different estimator that I'm proposing. You can show that E of S square is actually going to be sigma squared. So this is called a sample variance. This is called sample variance estimator. Okay, so I guess I have to once go through the entire calculation once again, just to make it clear to people. I'm sure people are lost here. So let's just go through this once again. See, what we have been doing so far, okay, is looking at MLE, okay, which is the maximum likelihood estimator. What we looked at is that it is essentially the probability that you see a particular data, okay, in the case of discrete. In the case of continuous also, it is like a probability, okay, because you have this interpretation that delta times fx is like a small probability around that point, okay. And basically maximum likelihood estimator is trying to find out what parameters best explain the data, okay. And the very nice example that you can use in real system, you can actually check this. There are actually legal cases where they have done something like this, okay. You look at the sample, you look at the population, and you find out that something has caused something bad to happen, and then you actually find that these kind of things have happened, okay. So in order to do the MLE estimate, what you need to do is basically you need to find out the likelihood and then take its derivative after taking the log to find the estimates. So these calculations you can do at home, okay. These are easy calculations you can do at home. The point is not the calculations. The point is that these calculations are kind of what you expect to come. And in the case of normal distribution for its variance, what it turns out is that the MLE is biased, okay. This idea of biased estimators is what you will see quite often in machine learning also, okay. What that means is, even when n tends to infinity, there will be some variation between the actual parameter and what you will learn, okay. So generally having unbiased thing is good. So it turns out that the MLE estimator for sigma is biased. Why is that? If you take the expected value of that MLE estimate, you should have got the true sigma, but you don't actually get the true sigma. And here is the calculation which shows that, okay. So I don't know if someone has any question here, but if you have, you do ask. And when you take the expectation, you will get n minus n 1 by n sigma squared. So that is the whole picture. So, and the corresponding estimator, which is unbiased, is called as a sample variance estimator. And this is, instead of taking the like the average, you are taking by n minus 1. Okay, that's the only difference between S square and your sigma MLE here. So here it is n, but here I am taking n minus 1. That's the only difference. Okay, and this is called as a sample variance estimator. See, the whole idea is this is going to be used at later point. All you need to do to understand this up till this in this class is to just understand that what it is trying to do. Okay, that's all I'm expecting here. We are not going to go to the next stage of machine learning and try to use it in some place. We are just trying to give you the foundation which will help you build on from here. Okay, so yeah, so that's about it. So let me just quickly check if everyone is okay with this. So can I have a last poll to see if everyone follows this? Yes. So any questions, please ask. I think you will help yourself and your classmates if you have a question. So Nishant, do you have a question? I see your hand raised. All right. All right, so that's about it. So there are few topics that I have not covered in detail, but I will just spend some time making a video on that. And I will try to speak loudly so that the next video recording is a little more clearer, but that's about it then. So we'll have the quiz next week. And the topics is basically whatever we have covered up until this point: Markov chains, and the weak law of large numbers, then central limit theorem, and so on. Okay. Yeah. So that's about it. Have a nice lunch. Thank you, everyone.